And we will move on to the last speaker of the session, which is Anastasia Georgievskaya. Can you hear us?
Yes, hello everyone.
Hello,
Hello
great to
Morten.
see you, and welcome back. You are a veteran of this meeting, and we're very happy to have you here. Whenever you're ready, you can share your screen, and we will enjoy your presentation.
Yes, thank you so much. Hello again everyone. A great pleasure to attend this conference again and again. And what's amazing about this event that every year you learn so much new about aging and latest advances. So thank you so much for bringing all these amazing scientists again this year. So today I'd like to talk about AI to confirm rejuvenation treatment success and the role of gender-specific scales in the performance evaluation. As a disclaimer, I will be talking about imaging data, so maybe this is not everyone was expected, but I hope it will be interesting for you to learn about different approaches, which I believe are really patient-friendly. So let's first talk a little bit about the motivation of us as individuals to invest, undergo, and study anti-aging. So first of all, I think every one of us is interested in slowing down aging. We're all interested in staying healthy. For most of us, it's important not to experience the deterioration of our cognitive functions. And still, for many of us, being perceived as a part of a younger group of individuals is also one of the motivations, which is sometimes stigmatized but by the society, but still it's something where is deep inside us that we want to stay younger and healthy. So when it comes to the actionable list of what we can do, so we can embrace different interventions, either changes of lifestyle or treatments. We can look deeper and try to fix broken mechanisms that lead to the aging of our body, and we can also modify some of the processes which are not broken, but that ultimately will lead us to staying healthy and younger. Whatever we're doing, it's still important, to have this motivation wherever it comes from. And some of the approaches can be more convincing to patients than others in doing that. As a person, we all might be asking, so is anti-aging happening? So is rejuvenation process happening? And here I try to, put some of the ideas how we can do that. So we first have clinical parameter evaluation, or we can know that, for example, this treatment was working for a model organism, which are more R&D friendly methods. So then there are a number of cognitive tests, functional tests, and even self-observation by a patient. But in the end, there is also, on the top of that, the most, I think, user-friendly method is using different aging clocks. That can be omics clocks, or this can be also photographic clocks. So here's the example of multimodal aging clocks, which are developed by our partners from Deep Longevity, who are utilizing such type of data like blood biological tests, transcriptome, microbiome, but also a number of everyday data like your pictures. This was developed in collaboration with HowDI, or different behavioral tests, or your mind age. And these clocks are incorporated into the product for the end consumer, which is called Young AI, which is mobile application and desktop application, but helps you understand why you age faster, or what you can basically do to try to revert your age. But today I'd like to focus on skin. So when it comes to skin, we would like to understand, so how do I compare? So does my skin age? So are there any indications on my skin that say that I'm aging? And once we know our age, let's say predicted by some deep neural network, we would like to understand, okay, but how am I performing compared to my group? So my reference group, that can be my ethnicity group, it can be my age group, or it can be my gender group. Today, I'd like to focus on their age group and gender group, and talk more about what's actually happening within these different populational groups. Some of the motivation why we decided to use imaging methods in our research. So obviously it's not the only methods that we can use. There are also sensorial data based on different type of sensors or biophysical evaluations, primarily different type of microscopies, preclinical assessment when an expert evaluates skin and says if it's looking better, if it's looking older, so what are the prominent signs of the aging process, and finally, imaging methods. So I tried to summarize some of our motivations. So for us, it was mostly important if we can have enough data, because computer vision methods and neural network basically primarily need a lot of data. Then it was important for us that we can have different endpoints. So we can have data for different ages, different gender and ethnic group. We also wanted to have a look at the methods that don't need any special devices, because in our study, we were using primarily selfie data, which was coming just from mobile phones. One of the disadvantage of using this data is that we need standardization, but this is also part that we algorithmically managed to solve with our system. So what our software was doing in this research, so first, as I mentioned, it's important to standardize the data. So for that, we use a library that we developed in HowTI to guide a user on how to make high quality picture. Then we use data quality assessment algorithms that utilize neural networks to detect primarily illumination, head position, over about 20 different parameters to ensure the data is standardized and we can compare different persons over time and that we can compare different individuals. Then we're making the data standardization that includes skin extraction. So we eliminate all objects that are not related to skin information to make sure that neural networks don't make predictions based on other objects. For example, the background or potentially what they see in the picture, which is not skin related. And finally, we calculate about 15 different large group of metrics, which we were using to evaluate their subjects in our study. So the results can be presented, visually. We have specific scales for all of the parameters. The principles of the algorithm is that we extract facial zones when we launch algorithm on the whole facial picture, then on every zone separately to drive their end metric. As I mentioned, it was important for us to make evaluation within different skin types. And one of the biggest challenges in skin imaging is the ability to work on melanin-rich skin. So to do that, our algorithms, which are primarily neural network based, as a pre-processing step, use decomposition of image into the different spectral channels that reflect the signals from different facial structures, primarily from hemoglobin and melanin, which is deposited in keratinocytes. The principle of this separation is that our skin has a structure where we have keratinocytes on the top and then blood vessels are underlying beneath that. And then where light hits our skin, the physical difference in location of keratinocytes and hemoglobin allows us to separate the signals, and we can do that pretty much for all other parameters, for example, collagen in our skin. So as a result of this processing, we're able to separate skin according to severity of every parameter agnostic to the skin tone. So in this picture, you see the uniformness, which reflects how flawless our skin is, separated into 9 different classes. And you see that it doesn't matter what type of skin is, we can do it equally good for all of their different skin types. So now let's talk let me now go to the experiment itself. So we used a private HowTI dataset, which consisted of high-resolution selfies collected with smartphones. In our study, we have pre-screened about 400 participants, 433 participants. The dataset contained both persons with fair skin tone and deep skin tone. The age range was between 18 to 67 years old, and we had slightly more females. So we had 244 females and 189 males in our study. So then we took all of these participants and we split them into 6 groups. So these were people younger than 30 years old, between 30 to 45 years old, and 45 years old and older. So the motivation to make the split in this way was to have within every age group have a more or less same number of the subjects. And before processing the data, all of these pictures were anonymized. So here are the examples of how these pictures in the data set looked before we started to process them for our experiment. And we used, initially the system can provide about 130 facial data points, but for the experiment, we selected only 10 out of them, and every parameter was scaled from 0 to 100, where 0 was the lowest score and 100 was the best observed score in the population. It means that the scores are relative. Then we had a look at the parameters that we had in the experiment. As I mentioned, we picked up 10 parameters out of more than 100, and we made some assumptions. So from their biology of skin, we know some parameters are changing more dynamically and some parameters change more time to change. And also there's an assumption that our skin quality, as pretty much every type of our body tissues, decline as we age. This is an example of the scores explaining how they were designed. So as I mentioned, we took the whole anonymized picture, then every algorithm which were presented by a neural network predicted submetrics which were unique for every parameter. For example, here we see pigmentation. So for pigmentation, we collected the number of spots, the density of spots on the face, and for example, spot intensity based on the signal from pigments. We made this calculation for every facial zone, and then using nonlinear transformation, we made the overall facial score. So here are the results. Again, to remind, we had 6 different groups. We had 3 groups for males and 3 groups for females, divided according to their age. And so the first assumption we wanted to test, is it true that parameter distribution in different genders and different age group is different? So it might sound like quite obvious, but to our knowing, none of the words before had evaluation of 10 parameters at the same time tested on the same data set. And indeed, we can see that the distribution of parameters is different. There are multiple reasons for that for different genders, primarily for males and females, their main contribution is based by the hormones and the genes. But also lifestyle, as we believe, will have an impact. It's well-known fact that females basically take more care of their skin. However, aesthetic interventions for males and products and cosmetics for males are no longer a niche segment. So there is significant growth in interest from males to also undergoing rejuvenation procedures. So this is why we now should also understand what are the scores and scales that can be applicable to them, so that we not just compare them with scales developed for females, but we compare them with scales that are suited best for this task. Then if you look at these graphics, the first question is that the distribution is not always same for males and females for the same parameter. So just to read this table right, so these are, it means that 2 graphics here relating to the sagging algorithm, and the CBIT distribution is quite different. All the graphics were also normalized to the size of their group. Then the second assumption that we made in this study is that most of parameters will decline as we age. And we were making an assumption that they will decline for both males and females, probably at a different pace because of the nature of the skin. So, for example, when it comes to skin texture, so skin is basically is thinner for females than for males, then obviously it will have a contribution. But when we looked at the parameters, it turned out that in fact not all parameters were changing as we age. So for example, if we look at the sagging parameter, yes, it did decline as the individuals had older age for males and females. But for example, dark circles, we couldn't say that this parameter will decline as we age, because pretty much all age groups had different scores from ranging from good scores to bad scores. Then we also saw that, yes, IBEX were declining. IBEX score was declining as the age. Obviously, wrinkles, perhaps one of the best examples when younger individuals have much less wrinkles than older individuals. It was quite interesting that pores showed that in younger age, our pore score is better than in older age. What was another surprise is the uniformness. So uniformness is a reflection of overall skin unity. So how if we have a lot of pigmentation and wrinkles, so altogether it contributes to the look of our skin. And interestingly, uniformness was not predictive of their age. So we see here that individuals in younger age and in the older age, they had different levels of uniformness. So one of the possible reasons and explanations that we came up with is that uniformness reflects several parameters at the same time, and probably for every individuals, the changes of parameters will be different. So this is why when we look at the overall uniformness, we see that it doesn't decline significantly as we age, and it's different in different ages. So then for pigmentation, we also saw that pigmentation is well predictive, like not predictive, but we see that it's better in younger age group than an older age group. Interestingly, pigmentation for males was shifted towards lower values in older age group, which was not the same for females. We also saw that redness, unfortunately, is not very indicative of the skin quality in different age groups, and translucency is also not a good parameter to be used as a potential biomarker. So to conclude, first of all, in this work, we showed that computer vision-based methods can be applied to selfies, which is, I think, quite important if we are trying to develop patient-friendly solutions that can be used in everyday life and don't require any specific equipment. And clearly, we saw a separation between different individuals and population groups. Obviously, very important that in this approach requires data standardization when we collect the data and before we process it. And we see that distribution of skin parameters for different age groups and ethnic age groups and gender groups was different. And out of the all 10 parameters that we used in this study, we concluded that wrinkles and pores can be used as potential biomarkers to evaluate the skin quality and potentially be used to evaluate different anti-aging interventions. I'd like to stop here. Thank you so much for your attention, and I will be happy to take the questions.
Thank you so much, Anastasia. Really interesting talk. I have a question. There's also a couple of questions on Slack, but with the ability to identify these features in the skin, have you tried to see how each feature, like wrinkles or sagging, how that impacts your age predictor? Can you remove those features and then see how, so do a sort of feature importance analysis?
Yes, thank you, Morten. Appreciate the question. Yes, we did a number of experiments when we used technique with a sliding window to occlude different parts of the face with different skin features and see what will be the predictions. In the end, we came to the conclusion that most predictive features were again, wrinkles and pigmentation. So it means that not only texture of our skin and the way our facial geometry changes or morphology, but also the color are predictive, and wrinkles and pigmentation are the most predictive features.
I see. Okay, great. There's another question from Slack, Yu Xuang Lu, who writes, interesting talk. I wondered, how would you make sure the photos are collected from patients are good enough to run all those analyses?
Thanks for the question. So there basically were two approaches to standardize pictures. The first approach is based on the data collection itself. So we used a library that analyzed light condition, head position, and resolution, which are the most essentials. But obviously on mobile device, you cannot put neural network algorithms just because there's not enough computational resources. So to do that, we just had additional neural network-based algorithms, which were trained on curated data labeled by annotators, and then we just sorted out pictures of bad quality. So we pre-selected good pictures to enter the study.
And is there any normalization occurring before the neural network analysis, like light conditions or something like that?
Yes, exactly. So we're primarily analyzing light and about 20 of other different parameters, and also we're making white balance correction. So this is all done automatically.
Okay, great. There's a question from Peter de Kaiser here.
Interesting talk. So to what extent does the acute state of the individual matter for your analysis software? And should you, for instance, take multiple images of the same face over different time points? For instance, yesterday we had open bar, so many people probably have now eye bags. Does this complicate your analysis, for instance?
Yes, of course. That's absolutely true. In addition to this, data standardization, there is also some natural variability in the algorithms, which, but for that, we came up with a solution long ago. So there is some error for every algorithm, and then within the error for every algorithm, we can say that there's significant change and that is not. So for every algorithm, we have this measured error, and then we would like to say that yes, there is some indeed effect that happens. We will have a look at the error that was tested under the development.
Very nice. Thank you, Anastasia. I definitely also feel a little bit older today than yesterday. Let's give Anastasia another round of applause.